This is Calculus 3, video lecture number 33 on surface integrals. So we've integrated functions of a single variable over intervals, probably feels like ages ago, functions of two variables over regions in the plane, functions of three variables over solid regions in space, and then most recently, real valued functions of several variables over curves and vector fields over curves. So now what we're going to consider is the integration of a function, f of x, y, z, over a surface, z equals g of x, y. And later in the section, we're going to consider integrating a vector field over that surface. But for now, we're just focusing on integrating a function over a surface. Okay, so how exactly do we go about doing this? Well, as before, we proceed by cutting up the surface, partitioning it, right? And you pick a point in each piece. Then you evaluate the function f at that point. You multiply that function value by the increment of surface. Your little increment of surface is ds. Then you add them up. Take a limit. Okay, so this is going to be a double integral. Why? Well, you're summing over a surface, right? So ds is a two-dimensional quantity. Now, since the surface, in this case I specifically said, is in the form g of xy, it's a function of x and y, then we know from before that ds is going to equal the square root of the partial of g with respect to x squared plus the partial of g with respect to y squared plus 1 dA. And as we considered in the previous lesson, if the surface is parametrized, then ds is going to equal, do you remember? I hope so. Magnitude of partial with respect to u crossed with partial with respect to v, dA. And dA is usually just du dv. Okay, so we're going to put it all together right now. Definition. The surface integral of f over the surface S is given by the double integral over S of f of x, y, z ds. Okay, so think back when we first talked about surface area, there was no function. We just had the double integral of ds, and that gave us the surface area of the surface. Now we're integrating a function over that surface. Now, if the surface is a function of x and y, then this integral becomes the following. So I can rewrite it as the double integral over d, where d is in the xy plane, and then you have f of x, y, and then I'm going to replace z with g of x, y, and then ds we know we can write as the square root partial of g with respect to x squared plus partial with respect to y squared plus 1 dA. Okay? And we can choose to integrate over a region in whichever coordinate plane is most convenient. So it could be the xy plane, it could be the xz plane, or the yz plane. You want to do what's going to be most convenient in the problem. How do you know? You look at the integrand. Okay, so I'm going to talk you through the next example. That way when you have to set it up on your own, you'll be able to reason through. Here's the first example. So evaluate the double integral over the surface S, x, z, ds, where S is the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we have a portion of a plane. That's our surface that we're going to be integrating over. As soon as I look at my integrand here, I see that it involves x and z. So it's a good idea if I keep everything in the xz plane. So when I'm choosing which coordinate plane to integrate over, I'm going to choose the xz plane. Okay, so first let's draw our surface. I'm going to draw the vertices that they gave us. Okay, so here's the z-axis, x-axis, y-axis. So it has vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. And I need the equation of this surface. I need the equation of this plane. Okay. Now remember, since they gave us all of the x, y, and z intercepts, there was a little shortcut way. We've talked about how to find the equation. You just kind of work your way backwards, right? So the equation is just going to be x plus y plus z equals 1. And then you don't have to fuss with finding the normal vector and all that stuff. Okay, well, since the integrand involves x and z, I'm going to choose to integrate over the xz plane, meaning I'm going to define D to be this triangular region here. Okay, so I'm going to draw D separately right now, the xz plane, the projection of this surface in the xz plane. So here's the z-axis, here's the x-axis, here's 1, 1. And this right here is D. Okay, very good. Now, this boundary right here on the upper part of D is defined by x plus z equals 1. Okay, and so what I want to do with the surface is solve for y in terms of x and z. So y would equal 1 minus x minus z, right? I don't want to have any y's in this integral. This is a double integral. So I want to keep everything in terms of x's and z's. That means ds is going to equal the square root partial of y with respect to x squared plus partial of y with respect to z squared plus 1 dA. And then this is just going to be square root of, well, partial with respect to x is negative 1 squared, it's 1. Partial with respect to z is negative 1 squared, it's 1. Plus 1 dA. So this is rad 3 dA. So I have ds. Now what is dA going to be? Well, it's either going to be dx dz or dz dx. It's up to us. Okay. In this case, I'll just put the limits for x on the outside. So x is going to be bounded between 0 and 1. And then z is going to be bounded above by 1 minus x and below by 0. So let's go ahead and set up our integral. So our double integral over s, right, our surface integral of xz ds becomes double integral over d of xz, and then I'm going to replace ds with rad 3 dA. Okay, let's take that rad 3 outside the integral, and then my limits of integration are going to be 0 to 1 for x, 0 to 1 minus x for z, and then I have xz dz dx. And then from here, it's just a really straightforward double integral, and you should end up with rad 3 over 24. Okay, nice. Now, as we've seen, many surfaces are best represented parametrically, where you have R, your vector valued function with parameters u and v, and then each of the components x, y, and z are defined in terms of u and v. So in this case, your surface integral would have the following form. So you'd have double integral over your surface of f of x, y, z ds. And then if you'll remember from the previous lesson, we'd have double integral over d f of, I'm going to replace it with r of u v, right? So I have to redefine my function in terms of u and v, no more x, y, z. And then ds is equal to magnitude of partial of r, our vector valued function with respect to u, crossed with partial with respect to v, dA. So that's ds for a parametrically defined surface. Okay, so let's look at an example here where our surface is defined parametrically, okay? So evaluate surface integral of rad 1 plus x squared plus y squared ds, where s is the helicoid, r of uv, defined with components u cosine v, u sine v, and v. We already dealt with this one, right? Do you remember? And they gave us the limits on u and v, so it's pretty straightforward to set up. I just have to figure out what those partials are and take their cross products. So partial of r with respect to u is going to have components cosine of v, sine of v, and 0. And then partial with respect to v will have components negative u sine v, u cosine v, and 1. And then partial with respect to u crossed with partial with respect to v. Let's see here. First component's going to be sine v. Second component's going to be negative cosine v. And the last one is u cosine squared v plus u sine squared v. Okay? And then this will simplify into sine v, negative cosine v, and u. Good. Let's take the magnitude before we set up the integral. Okay, do as much tidying up as possible beforehand. So you have magnitude now of this cross product. So that's going to be the square root of sine squared v plus cosine squared v, that's 1, plus u squared. Okay, so what does that tell me? That means ds is equal to the square root of 1 plus u squared dA. dA being either du dv or dv du, depending on how we set it up. Okay, so back to the original problem. Our double integral over s of rad 1 plus x squared plus y squared ds is going to become double integral over d, and then I'm going to have rad. Now be careful. Instead of 1 plus x squared plus y squared, right? Look at this. X is u cosine v, y is u sine v. So that means x squared plus y squared would just equal u squared. So I have 1 plus u squared instead of x squared plus y squared. And then ds is equal to rad 1 plus u squared dA. That's ds. Oh, good. Now the radical's gone, so we don't have to do that trig sub the way we did in the previous lesson when it was just surface area. I'll set it up with limits for v on the outside. So we'll go 0 to pi, 0 to 1, because u was the only variable in here. Then we're going to have 1 plus u squared du dv. And then this integral is pretty straightforward. So you should end up with 4 pi over 3. Okay, very good. It's almost easier when they're already parametrized for you, right? The surfaces? I think so. Okay, let's take things to the next level. On more complex surfaces, it's often necessary to use several integrals. So we're going to evaluate surface integral of xy ds, where s is the surface of the solid enclosed by x squared plus z squared equals 1, y equals 0, and x plus y equals 2. Okay, so x squared plus z squared equals 1. That's a cylinder, right? Opening on the y-axis. Y equals 0, that's just the xz plane. And then x plus y equals 2, that's another plane that's going to cut our cylinder. So it sounds like we're going to have 3 different surfaces, right, that enclose this solid. Let's sketch it out just to be sure. Let's start by drawing the cylinder. since it's opening on the y-axis and also y equals 0 is bounding part of the solid, I'm only going to include the positive y-axis. Okay, so there's the y-axis, and then straighten her up. Here we go. And then here's the x-axis. Good. And z-axis. Okay, so we've got x squared plus z squared equals 1. So let's scale this out. That's 1. That's 2. There's negative 1. 1, 2. So I'll start off by drawing the cylinder. So circle in the xz plane, then now let me project it parallel to the y-axis. The precision is necessary with these problems just so that your graph comes out nicely. Okay, so here we go. Okay, there's our cylinder. And then also, I'll draw in that y equals 0 is bounding part of the solid, the xz plane. And then x plus y equals 2. So that's another plane that's bounding our solid. Let's see. I'm just going to draw the line x plus y equals 2 in the xy plane. And then imagine projecting it parallel to the z-axis. It's going to come and cut through, right, our solid. So it'll cut it at an angle, something like that. Okay. Good. So you could imagine here, now there's going to be 3 different surfaces bounding our solid. We have the portion that's determined by the cylinder. I'll call that surface 1. Then I have the portion determined by y equals 0. And then lastly, I have that portion determined by the plane x plus y equals 2. All right, very good. So we have to do 3 different surface integrals and then put them all together. So the first one, let's deal with the cylinder. Now, one reason we studied how to write parametric representations of surfaces was precisely for this moment. So I can express the equation of the cylinder opening on the y-axis by using the parameters theta and y. So they have to trace out the circle x squared plus z squared equals 1. So I'm going to let x equal cosine of theta, y is going to stay y, and z is sine theta. We actually dealt precisely with this example in the previous video. And then theta should range between 0 and 2 pi. And then be careful for your limits on y. Okay, now look here at the cylinder. Obviously y is bounded below by 0, but y is bounded above by the plane, right? So y does not hit a constant every single time. If you're looking, stand in the xz plane and look in the direction of the positive y-axis. What's determining the upper limit? It's that plane. The plane's equation is x plus y equals 2, which is y equals 2 minus x. And if I'm letting x equal cosine theta, then that means the upper bound on y for this integral should be 2 minus cosine theta. All right, good. Now let's go ahead. We'll take our partial derivatives. So I'll take the partial derivative with respect to theta first. It doesn't really matter because you're going to cross them and take the magnitude anyhow, right? We'll have negative sine theta, 0, and cosine theta. And then I'm going to take the partial derivative now with respect to y. So I'll have 0, 1, 0. Oh, what a nice pair of vectors. Okay, so this cross product will yield, let's see here, that's 0 minus cosine theta. Next component's just 0. And last one is negative sine theta. Good. So the magnitude of this cross product is just lovely. It's 1. So now let's go ahead, set up our integral. That should be a theta in case you couldn't tell, sorry. So we have surface integral for surface 1 of xy ds. So I'll put limits for theta on the outside since those are constant, so 0 to 2 pi. Then limits for y next, so 0 to 2 minus cosine theta. And then in my integral, I need to replace x with how it's defined parametrically, so cosine theta times y. And then ds I know is going to be 1 times dy d theta. All right, nice. Now let's go ahead, evaluate this integral. So I'll have 0 to 2 pi cosine theta times y squared over 2, right? I'm going to anti-differentiate with respect to y from 0 to 2 minus cosine theta d theta. And then this is going to give me 0 to 2 pi cosine theta times a half. And then if I square 2 minus cosine theta, we'll have 4 minus 4 cosine theta plus cosine squared theta d theta. And then I'll let you play around with that. You should get negative 2 pi. Love it. Okay, let's move on to surface 2, shall we? So surface 2, you're going to like this one, don't worry. Surface 2 is defined by the plane y equals 0, right? It's right here, this back portion of the solid. Well, if y is equal to 0, and remember, we're evaluating the double integral on this surface of x times y ds. Well, on this surface, y is equal to 0. So if you integrate 0, you just get 0, and we're done. I told you you'd like that one. Okay, last one, surface 3. That was the plane x plus y equals 2 that came in and cut that cylinder, right? X plus y equals 2. So this one's going to be pretty easy if we just want to solve for y in terms of x, right? So y equals 2 minus x. And why am I happy doing that? Because remember, my integrand was xy. So I want to keep everything with x's and y's if possible. That's why for surface 1, we didn't want to get z in there, so we parametrized it instead. All right, so ds is going to be the square root partial of y with respect to x squared plus partial of y with respect to z squared, he's not there, plus 1 dA. So this is going to be the square root of negative 1 squared plus 0 squared plus 1 dA. So we get rad 2 dA. Okay, so let's go. Surface integral for surface 3 of xy ds is going to equal rad 2 double integral over d. What's d? Surface 2 is this purple ellipse, right? And you can choose to integrate over whatever plane is convenient for you. We were dealing with the xy. In this case, it makes the most sense if we go polar and project this along actually the xz plane, because we just have a nice circle in the xz plane, right? So we'll probably switch to polar in a hot second. Then I'm going to have x times y, so that's x times 2 minus x dA. Okay, go polar from here. So then now we're going to have rad 2. My region D is in the xz plane, so we're going to go 0 to 2 pi, 0 to 1. When I distribute x times 2 minus x, that's 2x minus x squared. Yes, and we're switching everything to polar. So that would be, here, I'll just leave it like that, 2r cosine theta minus r squared cosine squared theta, r dr d theta. Okay, so the worst part's done. and then you should get negative pi rad 2 over 4. Whew. All right, so we have to put it all together now, all three surface integrals. So the surface integral over S, including all three surfaces of x, y, ds, is equal to negative 2 pi plus 0 minus pi rad 2 over 4. I don't know, do you feel like getting a common denominator? I'm not in the mood. So negative 2 pi minus pi rad 2 over 4. It wouldn't necessarily make it look a whole lot better. Use your discretion. Okay, so we've done a few examples now of integrating functions over surfaces. But remember, I told you we were going to look at integrating vector fields over surfaces. Well, that is called Flux, all right? First, let's talk about what is Flux and how we are able to evaluate it. First things first, we have to restrict ourselves to orientable surfaces, surfaces that have an orientation. What kind of surfaces are not allowed? Something like a Mobius strip or a Klein bottle. If you don't know what they are, just search them. They're cool. They do not have an orientation. Non-orientable. So you want to be able to say which way is up, which way is down, which way is outward, which way is inward. You can't do that with these kinds of surfaces. So here's the idea. We're going to talk about a special kind of vector field, F, defined to be rho times V. So rho is going to be the density of a fluid. And it's measured typically in grams per centimeter cubed. Okay, and then V is the velocity vector field of the fluid. And typically that would be measured in centimeters per second. Or if it was in meters per second, then make sure rho is measured in grams per meters cubed, okay? So our units on rho V would be grams per centimeter squared per second. Now what we want to do is look at how fluid is flowing. So one more thing about this surface S, S has to be a permeable surface, meaning our fluid needs to be able to flow through it or penetrate. Okay, now here's a new vector n. N is a unit normal. Okay, needs to be unit normal. Vector to the surface. And if I consider rho v dotted with n, remember, since n is a unit vector, this is giving me the scalar projection of rho v along n. Well, what does that represent? That scalar projection, that's the amount, right? It's not going to be a vector, amount of fluid in grams per centimeter squared per second flowing in what direction? Normal to the surface. So if I take that scalar projection and integrate it over the surface, what does that represent? Well, let's look at the units and play around with it. It would be grams per centimeter squared per second. ds is 2 dimensions, so that would be in centimeters squared. So I would end up with some quantity that's being measured in grams per second. So this is the rate, right? It's a rate, grams per second, rate of flow of the fluid through the surface. Which is called flux. Okay, beautiful. So if F is a continuous vector field defined on an oriented surface S with unit normal vector n, then the surface integral of F over S, which is also called the flux of F across S, is given by the following surface integral. So you would have surface integral of f dot, now notice here, be careful, this s is a bold-faced s, meaning it's a vector quantity. But then if I take f dot n and then I integrate with respect to s now, ds is no longer a vector quantity. It's just your surface integral. And you can represent flux with capital Phi. Okay? Very good. Now, unless otherwise specified, the standard or positive orientation of a surface is upward. So if you have like a plane or something, then upward is the standard positive orientation. If you have a closed surface, then the standard positive orientation is outward. Okay, now, if your surface is a function of x and y, what do? Well, you could just set it to 0, so z minus f of xy equals 0. And then your normal vector to the surface would have components negative partial with respect to x, negative partial with respect to y, positive 1. This would be upward, this normal, since the z component is positive. Sometimes you're going to need downward orientation. So all you would do is switch the sign on all the components. You would use partial with respect to x, partial with respect to y, and then negative 1 if you need to work with a downward orientation. Why would you work with downward? Because that would be the way outward is going for some closed surface. We'll get to an example, don't stress. So suppose you had a vector field F with components P, Q, and R, okay? Well, then let's see how this flux integral is going to work out. You have integral over your surface, F dot n ds, and then remember we integrate over some region D. F has components P, Q, R, and then remember n had to be a unit normal, yeah? So the components would be negative partial with respect to x, negative partial with respect to y, 1. To make it a unit vector, I got to divide by the magnitude. So I'm going to have square root partial with respect to x squared, partial y squared, plus 1. Now hold on. What's ds? What's ds? ds is the square root of partial with respect to x squared, partial y squared, plus 1 dA. This is ds. So what happens in practice? You don't have to worry about making n a unit vector since the magnitude will cancel out with the corresponding quantity in ds. Isn't that convenient for us? Okay, just be super careful when you switch from ds to dA that you also switch from s to d appropriately. Yeah? They have to be matchy-matchy. So if you have s, you have ds. If you have d, that's when you have dA. Pay attention to stuff like that. Good. Are you ready for an example? I hope so. It's happening. So find the flux of the following vector field over the portion of z equals x squared plus y squared minus 9 that's below this little rectangle here, 0 to 2 in the x direction, 0 to 1 in the y direction, oriented downward. So they told us they want it oriented downward. Got it. Okay, what is this surface? It's a paraboloid, and it's been shifted down 9 units. Okay, and I could think of this as my function of x and y, correct? Okay. So here we go. Let's graph it out and see exactly what's going on. So in the xy plane, when z is 0, this is going to trace out a circle, right, of radius 3. X-axis. Y-axis, z. So 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so we've got this circle here. And then it's been shifted down 9 units, so that's where the vertex is going to be. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Something like that. So they want us to figure out what the flux is. I can't handle this piece here. It looks gross. Hold on. Okay, much better. The flux that's below the rectangle from 0 to 2, 0 to 1. Okay, let's sketch it out. So in the x direction, it's going to come out to here, right? 0 to 2. In the y direction, it's going to come out to 1. Well, the surface doesn't exist there, but basically they want to know how much fluid is flowing through the surface at the corresponding patch. You know, maybe it's over here somewhere. What's the rate of the fluid flow through there? Just project it down. Okay, so since it looks like I can define z in terms of x and y, I'm going to replace z with x squared plus y squared minus 9 in my vector field. Okay, so I'm going to rewrite f, because remember, these are double integrals, so you don't want 3 variables going on. When you're doing flux, it's a surface integral, it's going to become a double integral. We've got to get it down to 2 variable land. Okay, so f has components, x squared y, negative 3x times x squared plus y squared minus 9, and then 4y cubed. So let's clean that up. So f is x squared y, negative 3x cubed, minus 3xy squared plus 27x, and 4y cubed. Okay, now I need normal vector. Normal vector comes from the surface, normal to the surface. Okay, so I need partial with respect to x, partial with respect to y, negative 1. Why did I choose z to be negative 1? Because they told me downward orientation, and the first 2 components will always have the opposite sign. Okay, so basically determine, does this need to be positive or negative? Determine that first, and then you know what the sign of the other 2 partial derivatives is going to be. All right, so partial with respect to x is 2x. I'm going from here. Partial with respect to y is 2y, and then negative 1. Okay, so let's set this up. So flux is going to equal surface integral over s f dot n ds. Make sure everything's taken care of. You can't leave this off. All right, make sure your notation is spot on. This equals double integral over d. I'm going to replace f now with x squared y, negative 3x cubed minus 3xy squared, excuse me, plus 27x, and then 4y cubed, and then I'm going to dot that with n, which needs to be a normal unit vector. So components would be 2x, 2y, negative 1, divided by magnitude of n, which we know cancels out with the magnitude right here times dA. So we just don't even mess with it. But no, that's what's going on behind the scenes, right? Okay, cool. Now we're integrating over a nice little relaxing rectangle in the xy plane. All the limits are going to be constant, so just set it up however your heart desires. Let's do limits for x on the outside, then limits for y. Now you're going to take this little dot product here. So x squared y times 2x, so that's going to be 2x cubed y. Move on to the next term, minus 6x cubed y minus 6xy cubed plus 54xy minus 4y cubed dy dx. And before you just dive in and start anti-differentiating, notice like these are like terms you can combine. So clean up, make life easier before you just go for it. And you're going to end up with 41. Okay, very good. Now, I'm sure you're wondering, what would we do if our surface is defined parametrically? Same basic idea. So remember, our normal vector to our surface was found by taking partial derivative with respect to u, crossing it with partial derivative with respect to v, and we want a unit normal. Okay, so n would be that cross product divided by the magnitude. And then our flux is going to be, again, surface integral f dot n ds, which becomes double integral over the region D. You redefine f in terms of u and v, dot it with, okay, this is n, yes? So we're going to dot it with partial u crossed with partial with respect to v over magnitude of that cross product. And then do you remember what ds was? This ds here, when your surface is defined parametrically, is magnitude of partial u crossed with partial v dA. So this is ds, and then just like before, the magnitude crosses out, cancels out. So again, you don't have to worry about it. Pretty nice, right? Good. So we're going to revisit the example that we did earlier of a surface integral, and now we're going to change it so that instead of evaluating a function, we're going to evaluate a vector valued function, so we're going to compute flux. So using the outward orientation, find the flux of the following vector field x, y, 5 over the surface of the solid enclosed by x squared plus z squared equals 1, y equals 0, and x plus y equals 2. Okay, I'm going to go steal our other picture and come right back because I don't want to redraw it. So remember, we had three surfaces here. Surface 1 was the cylinder. Okay, I'm just going to draw box myself. How about that? So the cylinder, remember, we defined that surface parametrically. So it was x squared plus z squared equals 1. So we used theta and y as our parameters. So we had cosine theta, y, and sine theta. And then we already took that cross product of partial with respect to theta and y. And notice in this case, the components came out to be negative cosine theta, 0, and negative sine theta. Now this normal vector is inward. How do I know that? If it's not obvious to you, just plug in something for theta. Like for example, plug in 0, okay? Then negative cosine theta, that would be negative 1, 0, 0, and you could see on the surface that would be pointing inward. And what I need for standard orientation, which the problem also reminded me, is an outward orientation. So what do? You just change the sign. So instead you're going to use for n, positive cosine theta, 0, positive sine theta. Okay, so let's compute our first surface integral. So on surface 1, f dotted with n ds. So it's going to become double integral over my domain, I'll say the region D1. Now your vector field, look at this. It's defined to be x, y, 5. Okay, so I have to come replace x with how it's defined here on the surface. X is cosine theta. Y is fine. 5 is fine. Dot that with n. N is cosine theta, 0, sine theta. And then now it's dA, yeah? Good. Now from here, let's see. Remember, we defined our limits for theta and y previously. So theta was bounded between 0 and 2 pi. And if you'll remember, y was bounded below by 0 and above by the plane 2 minus x, which is 2 minus cosine theta. So limits for theta have to go on the outside because those are the only constant limits we have. So we'll have 0 to 2 pi and then 0 to 2 minus cosine theta. And then let's go ahead and take this dot product. So we'll have cosine squared theta plus 0 plus 5 sine theta dy d theta. Okay, and then I'll let you play around with this. You should get 2 pi. So that's the flux from that vector field on this surface. Okay, surface 2. Surface 2 was the plane y equals 0. So my vector field, again, go back. Your vector field has components x, y, 5. Well, on the surface y equals 0, your vector field is going to become x, 0, 5. And what's normal to the plane y equals 0? Well, remember, your standard orientation has to be outward. So outward from the plane back here, this one, that's y equals 0. Outward would be a vector going in the negative y direction. I want a unit vector. So just define its components to be 0, -1, 0. All right, now f dot n on that surface is going to be 0 plus 0 plus 0, which is 0. So the flux on that second surface, y equals 0, is going to be 0. Good. All right, one more surface to go. So surface 3 was the plane x plus y equals 2. And I can solve for y in terms of x and z technically, right? Y is a function of x and z, which is 2 minus x. So if I want a normal to this purple surface out here, the one that's shaded in, the slanted surface that was determined by the plane x plus y equals 2, I'll go ahead, take my normal, find the normal by taking the partial derivatives. So I'll have negative partial with respect to x, 1 negative partial with respect to z. How do I know that the y component needs to be positive 1? Well, remember, your standard orientation that you're asked for here is outward. So think, what's outward from here? Outward from here would have to be in the positive y direction. If y was negative, that would be inward. Okay, good. So let's go ahead, take our partial derivatives now of 2 minus x. And we're going to have partial with respect to x, but then the opposite of that, so positive 1, and there's no z, so that's 0. Now my vector field, remember, is x, y, 5, but on this particular surface, it's going to be x, y is 2 minus x, and then z can stay 5. So surface integral on surface 3 is going to be f, so x, 2 minus x, 5, dotted with n, 1, 1, 0, ds, which becomes double integral over region D3. And then let's take this dot product. I get x plus 2 minus x plus 0. And now this is dA. Okay. And then notice here, you know what, I should have a rad 2 here, because that rad 2 is included in the ds and cancels out. Okay, then notice here the x's cancel out. So all I am left with is double integral for the region D of 2 dA. Well, where is D? Okay, be careful. Y was defined in terms of x and z, yes? So that means D is in the xz plane. And if I just have double integral of 2 dA, that means my answer, or the result, is going to be 2 times the area of D. Well, what is D in the xz plane? Go back and look. Remember, it's that unit circle. X squared plus z squared equals 1. So this is the circle. in the xz plane. Radius is 1, so area is going to be pi. So 2 times its area, 2 pi. Whew, we didn't even have to actually do an integral. Fantastic. So putting it all together, are you ready? Total flux. Total flux is going to be 2 pi plus 0 plus 2 pi, which is 4 pi. And that concludes the lesson. We're in the home stretch. Don't forget to give it a thumbs up and subscribe. And stay tuned. Stokes' theorem is coming up next.